Do you guys want to start with some questions and stuff? Allie? Yeah, sure. Okay. So, here it's asked, can you guys stop talking, please? Thanks. I got a bit of a sinus headache going on, and I would prefer not to have to, like, kind of try to talk over top of us. So, if you can help me out a little bit there, that would be super swell. Just find what I'm looking for real quick here. So it says here for number 2, find secant alpha if cosecant alpha equals -3 and cotangent alpha is positive. So what I am going to be using, or what I'm going to do is I'm going to look for an identity that involves just cosecant and secant. Now, what am I going to find here? Nothing. So I'm going to say, okay, well, can I find an identity that involves cosecant and cotangent? And yes, I can do that if I look at the second Pythagorean. I have this. So 1 plus cotangent squared alpha is going to equal -3 squared. So I would say cotangent alpha then is going to be the square root of 9 minus 1. And since I square rooted both sides, that's really plus or minus. And since I know cotangent is positive, I know that that's really just the square root of 8. Okay there? Now I can say, okay, can I find an identity that relates secant, cosecant, and cotangent together? Yes, I can. I have that cotangent alpha is equal to cosecant alpha over secant alpha. Okay with that? So if I multiply both sides by secant and then divide by cotangent, so I have like -3 over the square root of 8. Or if I want to rationalize my denominators, that becomes like -3 over 2 root 2 or -3 root 2 over 4. That's probably the way it's represented in the back. Oh, it's not an odd. Silly Mr. Kulik. Allie, are you okay with what I did there? Great. Number 8? Sure. Okay. 10 you meant. Okay. We'll do 10 then. All right, I can do this in like 3 steps. So when I look at 10, typically the first thing I do is look for something algebraic. See anything algebraic? I do. If I look at these, do you notice that there's a greatest common factor? Yeah, what's the greatest common factor? How about just tangent? Right? Becomes like 1 over cosecant squared plus 1 over secant squared. Cool with that? Why is that great? What's 1 over cosecant squared? Sine squared. What's 1 over secant squared? And what's sine squared plus cosine squared? That's 1. So this just turns into tangent. Now that's the easiest way to do it. If you turned everything into sines and cosines, you could get there. It's going to be a little bit messier, but it'll work. It'll get you the same spot. Oh boy, that was pretty slick. You liked it, didn't you? You want to do 8 also? Sure. So first things first, let's see. Do you notice anything algebraic to do? Yeah, like reduce the fraction. Absolutely. Next thing I'm going to worry about is I got to get the variables the same, right? What is tangent of pi over 2 minus x equal? That's cotangent. Everybody's okay there? No, we can do better than that. So what I'm going to do is I'm going to kind of think about this as like cotangent x times 1 over cosecant x. Cotangent is cosine over sine. And 1 over cosecant is just sine over 1. So I can just get cosine x out of that. How'd you like that? It always looks so easy when you do it, Mr. Kulik. It's because I've done it again. Think about it, just put it this way. I've been a math teacher for like 15 years. So I've basically done this class every year for 15 years. Imagine how good you'd be at something if you did the same thing over again for 15 years. You'd look really good at it, right? That's a lot of practice. That's what it looked. That's why math teachers make it look like it's so easy. It's because like you've done it so many times, it's like that easy. You know what I mean? 11 on the same sheet? Okay, sure. Ah, I see. Okay. Do you see anything algebraic that you'd want to do here? No, I don't, right? Okay, identities. Is there a good identity thing that you see? Chanel.
Sine squared beta plus cosine squared beta is 1.
Yeah. And then do you see any more identity things? 1 plus tangent squared is an identity. That's secant squared. Oops, I put a squared there. That wasn't a squared there. And then it just reduces. How frustrating is it when it's like, I spent 20 minutes looking at that and I didn't make any progress, and you did it in like 30 seconds. I know, guys, the time that you spend on it, that will pay off, I promise. Like all the ways that you learn how to not do it, that's not worthless time, right? Like you found a way that like, oh, that doesn't work. Oh, I can't do that. Like that's bad algebra. Honestly, doing stuff like this, I think, teaches you more about algebra than you learn in your algebra class, because you're really kind of punished for doing like illegal algebra moves. Like you'll just not be able to get to the right answers. So I think in a way, it's like super helpful and super instructive, which is exciting, right? I love learning algebra. So exciting. What's next? Happy to spend some more time. I know this isn't easy what I've asked you to do. If you have more questions, I'm happy to spend more time. Or if you want to be like, hey, this is what I was doing, like, and I got stuck here. Madison. Sure. So first things we usually typically do are we're going to look for algebra things, right? But there's no algebra to do here. You agree? This is going to be the first thing that I'd want to straighten out. What is cosine of pi over 2 minus alpha?
Sine.
Yep. Okay. And then the next thing, I mean, you could add these two together, sure. You good with that? But we still have this tangent alpha times cosine alpha. Well, tangent alpha is sine over cosine. So I have 2 sine minus 1 sine, which is just 1 sine. And we're done. Whoa! How? Yeah.
Do you want to even from 47 to 62?
Sure. Do you have a preference on which one of those you'd like to see?
Not really, because I got all.
You got all of them wrong? Oh, no. Oh, no. That happens, though. Sometimes, like, it's got to get worse before it gets better.
Yeah. So that's just what I got.
All right. So Christian's established that he doesn't care which even one we do. Is there someone else that's interested in one of these particular even ones so I can 2 bird 1 stone it? Chanel.
56.
56 is a tricky one. So again, if you go back and you look back to the lesson, I suggested there was like some things that are helpful hints on getting started on these things, some guidelines. So one of them is that this difference of 2 squares is useful. And then number 6 is mindful of where you're trying to get to. So I just wanted to point that out before we get going on this. If I look at 56 here, I'm looking at the numerator. I'm going to work on the left-hand side because it seems like I'd rather start there than the other way, or the other place, because they seem equally bad, but at least the left-hand side seems like more I can do. Anyway, so I look at that, and I notice, hey, it's like a difference of 2 squares, but it's with division instead of multiplication. You guys see that? Okay. So I'm probably either going to multiply the top by sine x plus cosine x. I meant multiply the top and bottom, or multiply the top and bottom by sine x minus cosine x, right? It's which one do I want to make the perfect square with, the numerator or the denominator? So to kind of make a guess as to which one I'd want to look at, I'm going to look over here. Which one of those two looks the most like a difference of 2 squares? The top one, because I have something squared minus something squared. Well, something squared-ish. The 2 is kind of a problem, but we'll figure that out in a minute. So that would be what I would see. Say, okay, so I want to make a difference of 2 squares with the numerator. So I'm going to multiply the top and bottom by that. So if I do that, I get sine squared minus cosine squared in the numerator. And then if I FOIL that out in the denominator, I get that. Everybody okay there? Okay, let's look at what we can do with this. One thing I like right away when I notice this is like, hey, that piece is in there. That's a really nice sign. That feels good, like that was supposed to happen. Like I made a good decision there because I got part of what I'm looking to get. What else do you notice we could do? Yeah, this right here is 1. So that gives me the entire denominator. Ooh, buddy, I feel like I made some good choices in my life now. You guys agree? Now I just got to figure out what to do there with the numerator. So I notice that I have 2 sine squared over here. I have only 1 sine squared over there. So I'm not going to change the sine squared part, because I know that needs to stay there. I need to get more of those. So I'm going to be messing with the cosine squared part. That's what I'm going to have to be changing. Everybody's okay with that reasoning? Well, I remember that sine squared x plus cosine squared x is equal to 1. If I subtract sine squared from both sides, I can say that cosine squared x is equal to 1 minus sine squared x. Everybody agree with that? So that's what I'm going to plug in for that cosine squared. So I still have the sine squared. And then in place of the cosine squared, I'm going to write 1 minus sine squared. And if I distribute the negative through, that's going to give me sine squared minus a negative sine squared. So that's going to be plus, giving me 2 sine squareds. And then minus of a positive 1 is negative 1. And that's what I need to end up with.
Sorry, how did you get the 2 sine squared x?
So I have sine squared minus a negative sine squared, which is sine squared plus sine squared. Is that okay? So again, the trickiest part here was deciding to do that. If you didn't do that as your first step, it's going to be tough to get there. You know what I mean, guys? Just was going to be tough to get there. Are you okay with the logic that I used in like looking at the problem at the start to figure out what I needed to do first?
So do you look at the numerator or denominator?
I'm kind of looking at both. I'm looking at whichever one it feels like I'm trying to make a decision about, like, because with the fraction that I'm given, it's like it should be pretty clear that I have to multiply the top and bottom by something, right? Because there's nothing else I can really do to that fraction algebraically. And there's no like identity that I can handily use to transform any of those things. So just like, what am I going to multiply the top and bottom by? So I'm just kind of looking at the numerator denominator to see, like, is there something that seems obvious to use? And I'm comparing it with what the other side needs to end up looking like. And just hoping for the best. Sometimes you just like pick something and try it. Should we do another one of these? Great. Which one do you want to do? Grunter. You said, mm-hmm.
Yeah. I'm trying to think about which ones I struggled on though.
Yeah.
Give me 1 second.
Half of 1 second.
Give me
Okay.
Just 1 half. All right, here we go. Already did 56.
58? Okay. So if I were doing 58, which side feels like the one you'd want to work on? I mean, come on, left-hand side, right? Like, it's crazy to do something else. Okay, everybody agree with that? All right. What do you think we should do first? Chanel?
I mean, you could try to like find multiply the denominators, get a common denominator.
Yeah, I think that making a common denominator is exactly what I would do there first. Since we have two fractions on the left-hand side and one single thing on the right-hand side, at some point, we'll have to add those fractions together. Everybody agree with that? And the easiest way to turn two fractions into one fraction is just a common denominator. So this first fraction will multiply by 1 minus sine x, and the second one by 1 plus sine x. So there we go. Everybody's okay with what I made there? What do you think we should do now? Hi.
Do you have an extra graphic calculator?
Sure. Are you borrowing this?
Yeah.
What's your name?
Kendall Smith.
Kendall Smith. Make sure you bring that back, Kendall Smith. Okay. What do you think I should do next? Chanel?
You could try foiling the common denominator.
Yeah, let's just multiply everything out and like see what we get, right? So we'll distribute in the numerator and then we'll FOIL down in the denominator. Now the denominator is nice because it's a difference of two squares, so the FOILing is really easy. And oh, look at this nice stuff. Boom, boom. That's all right. And then I have cosine x plus cosine x left in the numerator. Okay. Well, that's good because guess what I see? I see the 2 that I'm supposed to be getting. That's righteous. All right, 1 minus sine squared. Is there anything I can do with that? That is cosine squared. Yeah, using that same logic we used back on, was it 56, right? And what can I do with that? Little reducey. Which is just 2 secant. And we're done. What'd you think on that one, Drew?
Yeah.
All right. Who feels overwhelmed? It's okay to say yes. Like, please give me honest feedback. Trying to be like, no, I got it. And when you don't got it is like, that's not helpful to me. Chanel?
I just have a question. What are the little red rectangles?
That's just like the period at the end of your proof that says like, I'm done proving stuff.
Oh,
So it just like symbolizes the end of one proof.
oh, okay.
You also see this that in commonly like in a magazine, like if your magazine has an article that runs multiple pages, when the end of that article is done, they usually use that same like filled in period for like, so you know the article's done and there's not more of it on like another page. You'll see that in magazines. Not that anybody actually reads print magazines much anymore, but it's a shared symbol. What else do you guys want to talk about? I know it's been a couple of days, right? You have to do some of this stuff on your own. It's not easy because there's not like, oh, you just always do it the same way. You have to have like a little bit of imagination. And then you have to have like good algebra skills that you don't make some like crazy algebra mistake, you know, and like reduce something the wrong way or like distribute an exponent and, you know, marry. Of course. All right. Which side would you want to start on? That makes sense to me. Let's start on the right-hand side. Okay. So if I think about this, the only stuff that I'm going to be changing is going to be that part. Because sine to the 5th is really sine x times sine to the 4th x, right? And we have that part already taken care of. So somehow that stuff in yellow needs to turn into a sine to the 4th. Okay. What does that stuff in yellow kind of look like? Kind of looks like a quadratic. Yeah, because there's 3 terms and there's like, you know, a constant term, there's something squared and then something to the 4th. Like that to me reeks of a quadratic. So if we say, okay, well, let y equal cosine squared. This is just like 1 minus 2y plus y squared then, right? Now, can we factor that? Yeah. What does that factor to? Oh, let's make it this way. 1 minus y squared, right? Everybody agree with that? So instead of y's, though, we have cosine squared x's. Oh, boy. Does that seem okay? What's this? And what's sine squared squared? Sine to the fourth. And what's sine to the fourth times sine? Sine to the fifth. And that's what we were looking for. Doo-doo-doo. Sneaky, Mr. Kulik. That factoring, wasn't expecting it. Algebra. You know, just algebra. You didn't expect to find it there. It's like, I didn't expect a factor in here. That's not fair. It's pretty fair. Pretty fair. You want to do some more? You ready to do something else? Well, we're not going to sit here staring at each other awkwardly. We're going to do one of the two things. Either have to ask more questions and give me more to work with, or we're going to start doing something else. You just want me to choose? Okay. We'll just do something else. That's fine. All right. So again, doesn't mean that you can't come back and ask questions about these ones again later. You certainly can still do that. That is A-okay. But for now, for today, we're going to circle our way back to section 5.2 and talk about solving trig equations. All right. So remember in last chapter we asked you to do things like find the exact value of theta equals sine inverse of 1/2, right? How did we do this? Before we did the unit circle, though, what should have we done? The range for sine inverse is negative pi over 2 to positive pi over 2, which is quadrants 4 and 1. Right? Where is sine of 1/2 or sine theta equal to 1/2? Where's sine positive? Quadrant 1 or 2. So where am I going to be looking at?
1.
Quadrant 1. So I go to the unit circle. I'm looking for the theta where the y coordinate is equal to 1/2. When I do that, what am I going to find? Pi over 6. Right? Everybody's okay with that? And then we, in chapter 4, asked you to do find the exact value of sine theta equal to 1/2, where theta's between 0 and 2 pi or something, right? Oh, I didn't do that yet. Sorry, we didn't do that yet. But we do sorry. Something like this, right? And give you 2 pi. Give you just 1 pi of stuff to find, right? So we did this, started the same way. Where is sine theta equal to 1/2? Still quadrants 1 and 2. What quadrants are covered from angles from pi over 2 to 3 pi over 2? It's quadrants 2 and 3, guys. Just shout them out when you know. We should still be pretty good at this. So what do? We go to the unit circle. We're looking for theta. In Q2, where y is 1/2. What do we find? 5 pi over 6. Now, what if we ask, what if I ask you to find the exact values, possibly, of sine theta equal to 1/2 on the interval from 0 to 2 pi? What quadrants are covered from 0 to 2 pi? All of them. Where is sine positive? 1 and 2. How many answers should we have? I'm going to have 2 answers, right? So go into the unit circle, looking for theta in quadrant 1 and quadrant 2, where the y is 1/2. We'd find thetas pi over 6 and 5 pi over 6. Everybody's okay with that idea? What if we did this instead? If I just ask you to find the exact values of sine theta equal 1/2. How many answers do I have here? I have more than 1. I have more than 4. Infinitely many answers to this. Oh no, why? Do I have a limit for how big I can get? No. So as long as I have 1 answer, I really have infinitely many, because why? Because you can keep adding 2 pi, find another angle that's coterminal till I have the same value of sine, right? Since there's infinitely many coterminal angles, and my answers can be as big as I need them to be or as small as I want them to be. As long as I have 1 solution, I'm going to have infinitely many solutions. Okay, so what do I do here? So we're going to solve it just over 1 period. So my answers, I know there are pi over 6 and 5 pi over 6. Just from the previous one, right? It's the same problem as before. Now, our answers is everything coterminal to those. how do I write that? I do like 2 pi k. Where k is just some integer value. So this is going to be super similar to what we did in chapter 4 here, right? The only difference being that we can now ask you for like any range of answers we want, right? The interval that we're going to be solving over can be infinite. Oh no, it's not that big of a deal. Let's do some examples. Let me actually pull up, oops, there. There. Now, why would it, I just moved it over here. Why would it go over there? I don't have to write these down every time, so I'm going to just do some screen capping. So find all the values of x on the interval from 0 to 2 pi that satisfy cosine squared x equals 1. Okay, well, what do I want to do here first? Yeah, we're going to square root both sides of our equation because if we're going to have to use one of our inverses or use an inverse function at some point, I got to do that. When I square both sides of an equation, what happens? Plus or minus. Very good. So this kind of like turns into two separate equations then, right? Everybody cool with that? And we're going to be solving both of these over 0 to 2 pi. So I'm going to go to the unit circle and look for all the places where x is equal to 1 between 0 and 2 pi. What do I find? Just happens at 0. Well, it does happen again at 2 pi, Mr. Kulik. Yeah, but 2 pi is not included in the interval that I'm solving over because I wrote a parenthesis and not a bracket. Oh, Mr. Kulik, you sly dog. Then we'll do the same thing over here. We'll go to the unit circle and look where x is equal to -1. Where does that happen at? Pi. Everybody cool with that? Not a big deal, right? Just basically doing the same thing that we have done before. Let's do another one. Are they going to get more complicated, Mr. Kulik? Well, what do you think, guys? Yes, of course they will. Okay. What if we have something that looks like this? What do you want to do first here? Divide by 3, yeah. Okay. Now what? Square root both sides. Okay. Then we're going to go and do what? Go to the unit circle and look for the place where the y has a 1 over whatever, and the x is a square root 3 over whatever. And it can be any combination of them, right? Because it could be positive or negative. So any place, whether it's positive or negative, that's what we're taking. So how many places should we be finding here? Should be 4, right? 1 in each quadrant. Everybody agree? Okay. So when I do that, I got pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. What if instead this was yeah, you mean integers. So you'd write it, oops. Does anybody notice anything about these answers here, though?
Not the same amount.
Yeah, that's true.
Exceeding the number of ones.
Look at this pair of answers. How far apart is 5 pi over 6 and 11 pi over 6? Pi apart. And how far apart are these pair of answers? Pi apart. So if I add pi to 6 pi, or pi over 6, I'm going to get 7 pi over 6. If I add pi to that, I'm going to get 13 pi over 6, which is coterminal to pi over 6. So I could combine these answers into one solution by, instead of going by 2 pi's, I'm going by 1 pi. That's pretty clever, Mr. Kulik. Will you mark me down if I don't do that on a test? No. But is Mr. Kulik going to do that on the answer keys? Yes. So this is the better way of writing your answer there. Yeah, sure. Everybody's okay with that? What if instead this was written as from like negative 4 pi to 6 pi? If I wanted the answers there. Well, I'm just going to take my answers here, and clearly 5 pi over 6 is between negative 4 pi and 6 pi. Everybody agree with that? And then I'll subtract 1 pi from that. Is that between negative 4 pi and negative 6 pi? Or negative 4 pi and 6 pi? Yes. And I'll subtract pi again. Is that still in between? Yes. So I'll do it again. Is that still in between? Yes. Okay, we'll do it again. Is that still in between? Yes. So we'll subtract again. Is that still in between? No! That's too small. Okay. Well, now we got into the bottom. Now we need to go up to the 6 pi. So we'll just do the same thing, but adding. So I get 11 pi over 6, and then 17 pi over 6, and then 23 pi over 6, and then 29 pi over 6, and then 35 pi over 6, and then 41 pi over 6, but uh-oh! Oh, that's still okay. No, that's not, that's too big, right? 40 divided by, yeah, that's bigger than 6, right? Too big! Okay, so there's all my answers for the first solution. And I do the same thing down here for this one, right? Is everybody okay with what I did there? So if I'm given like a weird interval to solve over, what am I doing? I'm just using my infinite solutions answer to generate answers until I find something that's outside of the range. That's all I'm doing. Is that okay with everybody? What I did there? It's just kind of annoying, but it's not like, you know, once you have the infinite answer, it's not really difficult. Is that okay what I did? Are you sure? Do we got it? Can you say something? It's okay? I don't want to like bulldoze through it, but like there's not much more to it than that. If you can get the infinite answer, that's the hard part. And really, the infinite answer is not even the hard part. The 0 to 2 pi answer is probably really the hard part. Now, let's do another one. I just want to justify why I'm giving you just the 0 to 2 pi ones. All right. Okay. Oh my goodness, Mr. Kulik, how do I do that? What does it look like? It does look like a factoring problem, yeah. So I'd start by getting it equal to 0, because I know to solve by factoring has to equal 0. So notice this is one of those factoring problems where the leading coefficient isn't 1. So you need to find the two numbers that multiply to give you the leading coefficient times the constant term. And then add to give you the null term. So it multiplies to give you -2 and adds to give you 1. I'm so embarrassed for you guys right now. Multiplies to give you -2 and adds to give you 1. Two and -1. Right? Now, do those two answers take you straight to the factored form? No! What do we use that with? What does that help us do? Yeah, we're going to use those to rewrite the middle term as 2 cosine x plus -1 cosine x. Right? And we'll make our two groups. Oops. When we make our two groups, must have a plus sign in the middle, right? What's my greatest common factor in the first group? 2 cosine x. Great. When I factor that off, I'm left with cosine x plus 1. Now I look at my second group. What's my greatest common factor? -1. Very good. That leaves me with cosine x plus 1. I know I factored correctly because those two pieces are the same. If I think about this as one thing and this as one thing, what is the greatest common factor between the stuff in the green? Cosine x plus 1. Excellent. When I factor that out, what's left? 2 cosine x minus 1. Woo! That was a workout. Now I can set each of these factors equal to 0. So I'm going to go to the unit circle and look for where the x-coordinate is -1. We'd solved that before. That happens at -pi only. And we'll go to the unit circle and look where the x-coordinate is 1/2. Where does that happen at? Pi over 3 and 5 pi over 3. Oh, not -pi. My goodness. Well, I mean, -pi is correct, but it's not in the interval that I was looking for. Pi is the one I wanted. So those are my answers. Everybody's okay with that? Boy, Mr. Kulik, this is starting to look a lot like Algebra 2 all of a sudden. Yeah, don't you know it? Don't you know it? Remember, you spent all that time in Algebra 2 solving polynomials, right? It's like the revenge of the polynomials are back. All right. Let's do another. Chanel.
May I go to the bathroom?
Certainly. What do you want to do first here? Move everything onto one side. That's a great idea. What is something you decidedly do not want to do in this case that's very tempting? Dividing by tangent. Yeah, why is that wrong? No, that's not the issue. If you divide both sides by tangent, these guys should drop out of there, right? Why can't I do that? Doesn't that make this life much easier to just do that? Tan x has a variable in it, right? So what value could it take? 0. Can we divide by 0? No. You're going to lose answers if you do it that way. Don't ever divide by a variable unless you're positive it cannot be 0. But certainly from 0 to 2 pi, tangent could be 0, right? Okay. So we did that. What next? Greatest common factor is tan x. Now I can apply the zero product property and set each of them equal to 0. So tan x, I go to the unit circle. Hello, little friend. There's a bug on my sleeve. And I'm going to look for the place where the y coordinate is 0, because tangent is y over x, right? Where does that happen at? At what? 0 and pi. Very good. And then over here, I get sine x equals 1/2. So I'm going to go to the unit circle and look for where the y coordinate is 1/2. Where does that happen at? Pi over 6 and 5 pi over 6. I mean, I thought we beat that to death there in the first set of examples where we got these answers over and over and over again. Here's the catch, though. I'm not done. What is different about this problem than any of the ones we've looked at so far? It has to do with tangent. What value can tangent take that sine or cosine cannot? It can be undefined, right? It can have an asymptote. Before I'm done, I have to make sure that my answers for sine are not extraneous, that they don't cause tangent to become undefined. Now, is that the case here? No, it's fine. Tangent is only undefined at like pi over 2 and 3 pi over 2. So like those are okay. But I do need to check those quickly to make sure they're not extraneous. Could they be? Yes, they could be. So I do need to be mindful of that whenever tangent and sine are together, or cosine or whatever are in the same problem together. You guys okay with that? And that goes doubly with like cotangent or cosecant or secant. All those things can be undefined places. So we do have to make sure that we're being mindful of our extraneous solutions. Now, this is not actually my answer because notice what is the question asking for? So what do I really need to do to each of these? Slap a 2 pi k on the end of them, right? Except these ones, I could really just use one of them and put a pi k on. And that's really my answer. Is this going okay so far, guys? What do you think? Uh-huh. You're so vocal today. I love it. Yes, you can go together if you want.
You're stealing my spotlight.
All right. Find all values of x that satisfy the equation 2 sine squared 3/4 x equals 1. All of a sudden here, things are going to get weird. What's different about this problem than any of the previous ones we've looked at? It's not just that there's a fraction, it's where the fraction is located. That's a coefficient on x. Remember back to when we graphed these things. Is this a C, H, or K? It's a C, right? What did C do? Which changes the period. So we're going to have to be a little bit careful about this as a result. We'll show you guys where in a second. Okay. So whenever you see a coefficient on our variable, we must be quite mindful. Okay. What do you want to start by doing? Great. And then square root both sides. Yeah, I heard you start saying it. Don't just shout them out when you know. Again, because we get a plus or minus when we do it to both sides. What's the square root of 1/2 really the same as, though? Root 2 over 2. So I'm going to write it that way just because it'll be more familiar when we go to our unit circle. So I'm going to go to my unit circle now. But here's the catch. I'm going to look for where y is either positive or negative root 2 over 2. But I'm not getting my answer for theta here. I'm getting my answer for x here. I'm getting my answer for 3/4 x is going to equal. So the places where that happens is at pi over 4, at 3 pi over 4, at 5 pi over 4, and at 7 pi over 4. And because we're doing this infinitely, we get that. Everybody okay with that? Okay. So have we solved for x? Yes. Certainly. Have we solved for x yet? No, man. Right? The x isn't by itself. What do we still need to do? Multiply both sides by 4 over 3. But that 4 over 3 needs to apply to here and to there. What do you guys think? Want to do a couple more like this? We got a couple minutes, right? Let me grab a good one. Ooh, that seems real early. All right. What do you notice? Coefficient on x, right? But they're only looking for answers between 0 and 2 pi, so that's a relief. All right, so I'll square root both sides. Everybody's good there. Go to the unit circle. Look for any place where x is positive or negative root 2 over 2. That happens at pi over 4. And it'll happen again at 3 pi over 4. And at 5 pi over 4. And at 7 pi over 4. Everybody's okay there? Katie? I went to the unit circle and looked for the places where the x-coordinate was root 2 over 2, or negative root 2 over 2. I'm just doing it in my head because it's math teacher, you know. So, and then we'll divide both sides by 3. So that's going to give me pi over 12 plus 2 pi k over 3. And that'll give me pi over 4 plus 2 pi k over 3. And that one will give me 5 pi over 12 plus 2 pi k over 3. And this one will give me 7 pi over 12 plus 2 pi k over 3. Now, what I'm about to do, it's probably going to be more helpful to have a common denominator between these two things. So I'm really going to write this as like 8 pi k over 12 instead of 2/3. It'll just make the arithmetic easier. Well, not, I guess not there. Well, yeah, I'll do that, and then I'll do this. Okay, because I want my answers from 0 to 2 pi, right? So I'm going to start with pi over 12. And if I add 8 pi over 12 to that, I get 9 pi over 12. If I add another 8 pi over 12, that gives me 17 pi over 12, still less than 2 pi. And if I do it again, I get 25 pi over 12. That's too big. On to my next answer. So I have 3 pi over 12, or pi over 4. If I add 8 pi over 12 to that, I get 11 pi over 12. If I add it again, I'm going to get 19 pi over 12. If I add it again, I'm going to get 27 pi over 12. That's bigger than 2 pi. Done with that one. Then we have 5 pi over 12. I'll add 8 pi over 12 to that. That gives me 13 pi over 12. Do it again, 21 pi over 12. Do it again, and I'm too big.
As we remember today, our marriage founder, one of the values of our marriage identity is about being a good listener. Ask yourself, how was I a good listener today with my friends, with the people around me? Lord, help us to be able to be good listeners to our friends, to our family members, to help us to understand their needs and allow us to respond to your Spirit, Lord. We ask all of this in your name. Amen. In the name of the Father, and of the Son, and of the
Hey, hold on a second, guys. Try 15 to 46. Be ready for a homework quiz on Friday this week, probably. Friday.
Thank you.
I know. I know. We're almost at break though, guys.
Thank you. I will not be here actually. Thank you.
Okay. If you want to try to do it early before you leave, that's okay. I'm just presenting the option.
Yeah, thank you.
You're welcome.
So if no one's on my thank you.
Take care, fellas.
If nobody else is online, on Saturday,
Yes.
is it going to be over like the 2 worksheets that we have? And then
I would say like 5-1 and 5-3. Not the stuff that we just did today.
okay. So then are we going to have a test after break?
Yeah. Yeah, we're not going to try to cram that in beforehand. That seems like nobody really needs that in their life.
Good. Right. Have a good day.
You too.